Hello and welcome back. In the last video, I talked about electrolytic cells and electrolysis. In this video, we will study a little about batteries, fuel cells and corrosion. So let's get started with batteries first. Any battery or cell that we use as a source of electrical energy is basically a galvanic cell where the chemical energy of the redox reaction is converted into electrical energy. However, for a battery to be of practical use, it should be reasonably light, compact, and its voltage should not vary appreciably during its use. There are mainly two types of batteries: primary batteries and secondary batteries. So let's look at primary batteries first. So what are these? In a primary battery, the reaction occurs only once, and after use, over a period of time, battery becomes dead and cannot be reused again. The most familiar example of this type is the dry cell, which is used commonly in transistors and clocks. This cell consists of a zinc container that also acts as anode, and the cathode is a carbon rod surrounded by powdered manganese dioxide and carbon. By the way, when you are reading these batteries, you have to know what the cathode is, what the anode is, what's the electrolyte, and what are the cell half reactions and the overall reaction. So what's the anode over here? The anode is a zinc container and cathode is a carbon rod surrounded by powdered manganese dioxide and carbon. The space between electrode is filled by a moist paste of ammonium chloride and zinc chloride. What is the paste made up of? NH4Cl and ZnCl2. So this is how the cell looks like, a rough sketch. We have a zinc cap, that is anode, and MnO2 plus carbon black plus NH4Cl paste, and a carbon rod as cathode. By the way, the images colors are inverted so that it looks nice on the dark background. In the book it may look different, but it's the same image and it doesn't really matter. So anode reaction is zinc giving Zn2 plus 2 electrons, and cathode reaction is MnO2 plus NH4 plus electron giving MnOOH plus NH3. So these are the half reactions which you should know also. In the reaction at cathode, manganese is reduced from +4 oxidation state to +3 state. Cathode is a site for reduction, so that's not violated even now. Ammonia produced in the reaction forms a complex with Zn2 plus to give ZnNH3 taken 4 times 2 plus. So this is a complex that is formed due to the production of ammonia. The cell has a potential of nearly 1.5 volts. So that was dry cell. Now there's another type of cell, that is a primary battery, which comes under primary battery, and this is also widely used. Why? Where do we use it? We use it for low current devices like hearing aids, watches, etc. And you might have seen it in your watch most probably. It's a small circular thing. It consists of zinc mercury amalgam as anode and a paste of HgO and carbon as cathode. So what's the cathode and anode for mercury cell? Anode is zinc mercury amalgam and cathode is a paste of HgO and carbon. The electrolyte is a paste of KOH and ZnO. Electrolyte is KOH, ZnO. So we have seen anode, what's a cathode, and what's the electrolyte. So now the half cell reactions. At anode, we have ZnHg, that's the amalgam, plus 2 OH minus, that comes from KOH, giving ZnO plus H2O plus 2 electrons. Anode oxidation. At cathode, we have HgO plus H2O plus 2 electrons giving Hg plus 2OH minus. So this is the half cell reactions for mercury cell. The overall reaction is represented by Zn plus ZnHg plus HgO. I repeat, it's ZnHg plus HgO giving ZnO plus Hg. It's a pretty simple reaction, right? When you add, things get cancelled here and there, and you end up with a simple reaction. That is ZnHg plus HgO giving ZnO plus Hg. The cell potential is approximately 1.35 volts. It remains constant during its life as the overall reaction does not involve any ion in solution whose concentration can change during its lifetime. And this is a rough sketch of a mercury cell. So it has cascade separator. Those things you don't have to know. You just have to know cathode, anode, electrolyte, half cell reactions. So now let's look at secondary batteries. So what do you think they will be? A secondary cell after use can be recharged by passing current through it in the opposite direction so that it can be used again. Primary batteries, we saw that after the cell dies we can't reuse it. So this is the differentiating factor between secondary cell and primary cell. So in secondary case we can recharge it by passing current in opposite direction. A good secondary battery can undergo a large number of discharging and charging cycles. The most important secondary cell is the lead storage battery, which is commonly used in automobiles and inverters. You might have seen one of the secondary batteries in your car. The car batteries are in fact secondary batteries, and you recharge it sometimes when the battery dies. So this is a sketch of lead storage battery in your right. It consists of lead anode and a grid of lead packed with lead dioxide, that is PbO2, as cathode. So anode is lead, cathode is a grid of lead packed with PbO2. 38% solution of sulfuric acid is used as electrolyte. The cell reaction when the battery is in use can be written as: at anode we have Pb plus SO4 2 minus giving PbSO4 plus 2 electrons. At cathode PbO2 plus sulfate ion plus 4H plus 2 electrons give PbSO4 plus 2H2O. The overall cell reaction consisting of anode and cathode reactions is Pb plus PbO2 plus 2H2SO4 giving 2 PbSO4 plus 2H2O. It's pretty simple again, right? So what do we do after the battery dies? We have to recharge it. So when we do this, the reaction is reversed. So when you are going to charge the battery again, we reverse the reaction, and PbSO4 on anode and cathode is converted into Pb and PbO2 respectively. Another important secondary cell is nickel cadmium cell, which has longer life than the lead storage battery, but it is more expensive to manufacture. And here comes a rough sketch of nickel cadmium cell. The overall cell reaction during discharge is given as Cd plus 2 NiOH twice giving CdO plus 2 NiOH twice plus H2O. We shall not go into details of working of the cell and the electrode reactions during charging and discharging, as they are a little complicated. So now let's look at fuel cells. Production of electricity by thermal plants is not a very efficient method and is a major source of pollution. In such plants, the chemical energy, that is heat of combustion of fossil fuels like coal, gas or oil, is first used for converting water into high pressure steam. This is then used to run a turbine to produce electricity. We know that a galvanic cell directly converts chemical energy into electricity and it is highly efficient. It is now possible to make such cells in which reactants are fed continuously to the electrodes and products are removed continuously from electrolyte compartment. So galvanic cells that are designed to convert the energy of combustion of fuels like hydrogen, methane, methanol, etc. directly into electrical energy are called fuel cells. One of the most successful fuel cell is reaction of hydrogen with oxygen to form water. So this is how it looks like. The cell was used for providing electrical power in Apollo space program. The water vapors produced during the reaction were condensed and added to the drinking water supply for the astronauts. Pretty interesting, right? So what happens to the cell? The cell, hydrogen and oxygen are bubbled through porous carbon electrodes into concentrated aqueous sodium hydroxide solutions. Catalysts like finely divided platinum or palladium metal are incorporated into electrodes for increasing the rate of electrode reactions. The electrode reactions are at cathode O2 plus 2H2O plus 4 electrons giving 4 OH minus, and at anode we have 2H2 plus 4 OH minus giving 4H2O plus 4 electrons. This looks pretty big, but the overall reaction is the famous reaction which you have seen in the lower classes. It's very simple, it's just 2H2 plus O2 giving 2H2O, a simple formation of water from H2 and O2. The cell runs continuously as long as the reactants are supplied. Fuel cells produce electricity with an efficiency of 70% compared to thermal plants whose efficiency is just 40%. There has been tremendous progress in the development of new electrode materials, better catalysts, and electrolytes for increasing the efficiency of fuel cells. These have been used in automobiles on an experimental basis. Fuel cells are pollution free, and in view of the future importance, a variety of fuel cells have been fabricated and tried. So with this we have completed batteries and now we also completed fuel cells. Now let's look at a common phenomena called corrosion. So it slowly coats the surfaces of metallic objects with oxides or other salts of the metal. The rusting of iron, tarnishing of silver, development of green coating on copper and bronze are some examples of corrosion. It causes enormous damage to buildings, bridges, ships, and to all objects made of metals, especially that of iron. So that's why we are going to study this topic in this unit. It is of great importance that you know how to prevent corrosion. We lose crores of rupees every year on account of corrosion. In corrosion, a metal is oxidized by loss of electrons to oxygen and formation of oxides. Corrosion of iron, that is commonly known as rusting, occurs in presence of water and air. So when does corrosion of iron, that is rusting, happen? You need presence of air and water for it. The chemistry of corrosion is quite complex, but it may be considered essentially as an electrochemical phenomenon. At a particular spot of an object made up of iron, oxidation takes place and that spot behaves as anode, and we can write the following reaction for anode: 2Fe giving 2Fe2 plus 4 electrons. Electrons released at anode spot move through the metal and go to another spot on the metal and reduce oxygen in presence of H plus. And where is H plus coming from? It is believed to be available from H2CO3 formed due to dissolution of carbon dioxide from air into water. Hydrogen ion in water may also be available due to dissolution of other acidic oxides from the atmosphere. This pot behaves as cathode with the reaction O2 plus 4H plus 4 electrons giving 2H2O. So we have two reactions for anode and one for cathode, one each. So the overall reaction is just the addition of these two, which is 2Fe plus O2 plus 4H plus giving 2Fe2 plus 2H2O, and the E0 cell for this reaction is 1.67 volts. So this is a rough sketch of what is happening. The two reactions which we have discussed on the top are given at the bottom, and there's nothing much in this diagram to worry about, so let's move on. The ferrous ions are further oxidized by atmospheric oxygen to ferric ions, which come out as rust in the form of hydrated ferric ions, that is Fe2O3.XH2O, and with further production of hydrogen ions. What is X? X is variable, so we don't know the water of crystallization, so we just give it as X. X is a variable, so rust is Fe2O3 plus XH2O, that is hydrated ferric oxide, and this further increases the production of hydrogen ions. So now we have seen what is prevention, and we also saw that it causes enormous damage. So how do we prevent it? Prevention of corrosion is of prime importance. It not only saves money but also helps in preventing accidents such as bridge collapse or failure of a key component due to corrosion. One of the simplest methods of preventing corrosion is to prevent the surface of the metallic object come in contact with the atmosphere. This can be done by covering the surface with paint or by some chemicals like bisphenol. Another simple method is to cover the surface by other metals like SN, Zn, etc. that are inert or react to save the object. So just a little more info on zinc. So when you use zinc to coat a metal, what exactly happens is the zinc gets oxidized, but it stops further oxidation of the object itself. So it acts like a preventive coating on the top. It doesn't allow further oxidation of the object. So this is how we are using other metals like Zn to prevent the corrosion of the object. An electrochemical method is to provide a sacrificial electrode of another metal like MgZn, etc., which corrodes itself but saves the object. So this is what I told previously before saying this point. This exactly happens with zinc, and this process of applying zinc coating to other metals like iron or steel is called galvanization. I don't want to talk much about this in this video. You can look at it in the internet if you are really interested at it. It's a simple process that is used widely in today's lives. With this, we have come to the end of this video. To summarize, we started off with batteries. First we saw primary battery where we saw dry cell and mercury cell. Then we saw secondary batteries. We saw lead storage battery and nickel cadmium battery. Then we learnt about fuel cells, and finally we saw corrosion. What is corrosion and how does it happen? What's its effect? Then we saw the chemistry of rusting, that is corrosion of iron, and finally we saw some techniques to prevent corrosion. With this, we have also come to the end of this unit. I hope you enjoyed the videos. Thank you and goodbye.